Now let's see how all these definitions and properties of the digamma functions work in real difficult integrals. So the integral in question would be the following thing. So you can put it, for example, in Wolfram Mathematica, and you'll be surprised by their unusual answer. So the answer is as follows: pi by 2 times the logarithm of 4 pi cubed divided by the gamma function to the 4th of 1/4. So let's try to compute this integral using what we have learned from our previous discussion of digamma function. Well, first of all, what we notice, the semi-infinite contour is much more difficult to deal with in comparison to their fully infinite contour. So let's try to analyze the integral, which is taking along the fully infinite contour from minus infinity to plus infinity. Can we actually reduce it to the original integral? And the answer is positive. We just need to specify which regular branch of the log function we use. And naturally, we understand this integral as the integral which is the contour integral, which runs above the corresponding branch cut, which defines the corresponding regular branch of our log function. So here is the branch cut, and here is our integration contour for this integral. And of course, it can be split into the integral from 0 to plus infinity and to the integral from minus infinity to 0. But let's actually switch to the representation of this x variable in their exponential form. So x equals rho times e to I pi for the negative part of the contour. And as a result, rho changes from plus infinity to 0. And we plug in this decomposition into our original integral and get logarithm of rho plus I pi. So the cosh is an even function. So here we just have cosh of rho again. And d rho, dx is turned into d rho with -1 sign. As a result, we get the following expression. First of all, the original integral is doubled because we need to change the differential, their integration limits, take into account this minus sign, so the whole expression is doubled. And we have additional imaginary part, which is very easy to calculate. It's a simple integral d rho over cosine hyperbolic of rho. And it is an elementary integral, and you can easily compute it and get the answer pi by 2. So this I1 integral, which is way more suitable to deal with because it's an integral taking along the full infinite contour, is in fact related to the original integral by the following simple transformation. So instead of dealing with the first integral, we'll deal with this I1 integral. Now, let's take this one. First of all, what we know from our experience with the theory of complex analysis, it's very inconvenient to deal with log function because they are multi-valued, and it's much easier to deal with power function. But there is no power function here, but we know that if we differentiate the logarithm, we get 1 over x function, which is a power function. So how can we differentiate, how can we introduce the differentiation into our integral? Well, the easiest step would be to differentiate the integrand with respect to some external parameter. Right now, there is no external parameter of the integral. It's just some kind of number, some number. And so the possible solution is to introduce the external parameter into the integrand and consider a modified. Naturally, if a equals 0, then it is reduced to our original integral. But now, the benefit of this introduction is that we can differentiate the integral with a parameter to get a much simpler expression to deal with. And of course, we need to think about the imaginary part of this parameter a. And for simplicity and for convenience, we assume that indeed this parameter has an imaginary part and it's negative. You will see in a second why it's so suitable. So now let's analyze this integral. The idea is that the modified integral can be computed exactly. And then integrating the answer with respect to a, we can restore I1 integral and hence the I integral itself. Right. So this integral in question can be easily taken using standard residue theorem. Indeed, it is a contour integral, and we can, it's an open-end contour, and we can close the contour with, say, semi-infinite, with infinite semicircle in the upper half plane of the complex plane of x. And this integral is reduced to the computation of the residues of the integrand. Well, naturally, since we have this hyperbolic cos function, it decays in the upper semiplane, as you're probably aware of, and the closed contour integral consists of the original integral, which is from minus infinity to plus infinity, plus the integral and the integral along this semicircle, which vanishes as r, the radius of this circle, tends to infinity. Right, and now we just rewrite this integral as a sum of the residues inside this contour of integration. The residues are defined by the zeros of the cosine hyperbolic function. Now we understand why this condition was very suitable, because if a is such that its imaginary part is negative, then we don't have to take this residue into account coming from this fraction. Right, so the zeros of the hyperbolic cosine function are simply pi by 2 plus pi n times I. So here they are. They're equidistant. And all of them are simple poles. And the residues of these functions are simply okay, so it's just 1 over pi by 2 plus pi n I plus a multiplied by the Taylor expansion of this cosine hyperbolic function. All right, so if we just figure out the expansion of this cosine hyperbolic near the residue, near the pole, sorry, and so you basically add very small epsilon parameter and see how the whole thing behaves as a function of epsilon. And what you get is just cosine hyperbolic of pi by 2 plus pi and I plus epsilon. So cosine of I z is equal to cosine hyperbolic, sorry, of I z is equal to cosine of z, and as a result, you get cosine of pi by 2. You can factor out pi n. It is turned into -1 to n, and minus I epsilon, which basically brings you sine of I epsilon. And once you analyze this, the behavior of this denominator, you immediately arrive at the conclusion that the residue is -1 to n divided by I. Now we know the residues, and we can write down the answer for this integral in terms of the following infinite sum. The sum of all the residues stretching from n equals 0 to plus infinity. So let's switch to the next slide to see how it comes about.